In this video, we're going to kind of really start to get at the heart of thermodynamics. Our real goal for this unit is to understand how we can predict whether or not a reaction is actually going to happen or not. We talked about this a little bit at the beginning, that we can write almost any chemical reaction on paper that can be balanced, it can involve real compounds, and it can still be utter nonsense that will never actually happen. And thermodynamics is one of the ways that we can understand why some reactions happen and some reactions don't. So we're going to start to answer this question of how do we actually predict that? And the short answer is that we need to determine if the reaction is what we call thermodynamically favored, which essentially just means, does the energy in this reaction move in the way that the laws of thermodynamics say energy should want to move? So we need to determine thermodynamic favorability. And right now we kind of have half of the picture. We've been talking about enthalpy, and enthalpy does play a role, but it is not the only factor. And so we're going to be talking about the other side of the thermodynamics coin, which is known as entropy. So enthalpy is important for determining thermodynamic favorability, but enthalpy alone does not tell you enough. So entropy accounts for the rest. So entropy is my favorite subject. Entropy is symbolized by a capital letter S, and a sort of typical high school definition for entropy that I'm not even going to write down because it's terrible and you should never use it, is that entropy is a measurement of the chaos or disorder or randomness in a system. This is how I was taught entropy, and I didn't understand it at all. I know what those words mean, but how do you measure chaos? And the answer is you don't. Chaos is not a quantifiable quantity, but entropy is. Entropy is something that we can calculate. Entropy is something that we can, calculate a delta S and plug into other equations to be useful to us. So a much better definition that I promise will make sense in a few minutes, it won't right now, bear with me. A much better definition of entropy is that entropy is a measurement of the number of possible microstates for a system. With something that has more possible microstates having a higher entropy. So, what the heck's a microstate? So a microstate is really just a way of arranging the stuff in your system. It is a unique way to arrange the particles and the energy in your system. So a really, really simple example, we're going to start with not chemicals. is if I imagine I have a container that has two compartments in it. Oops, that's not what I wanted to do. If I imagine that I have a container that has two compartments in it, and I have two different items that I want to store in this container, blue one and a pink one. There are two different ways that I can arrange those items. I can either put the blue item on the left and the pink item on the right, or I can put the pink item on the left and the blue item on the right. So these are different ways to arrange the particles in the system. So my particles are the pink and the blue things. The system in this case is my imaginary little container here. So these would be representations of two different microstates. Two different ways we can arrange the stuff in this system. And the more microstates we have, the higher the entropy of our system is. For chemical reactions, we can actually usually predict how the entropy is changing throughout the reaction. So whether the products are higher in entropy or the reactants are higher in entropy. And there are a couple major things that factor into that decision. So we usually only need the balanced equation. So for chemical reactions, we can usually predict the sign of the entropy change, which is delta S. Just from the equation. So there are a few different factors that affect whether delta S is negative or positive. Delta S is negative when your reactants are higher in energy than your entropy, than your products, that you're starting out at a high entropy and ending up at a lower entropy, so our change is negative. And delta S is positive when our reactants are lower in entropy, than our products. And there are two main factors that we want to look at to determine which side is higher, whether we have more entropy on the reactant side or more entropy on the product side. So the first thing that we want to look for, so factors affecting entropy, one thing that we can look for is the number of molecules on both sides. Generally speaking, more particles is going to have higher entropy. Remember that higher entropy corresponds to more microstates. So if something has a higher entropy, it must have more possible microstates. So we saw a minute ago this simple two-particle example that if we have two particles in a container with two slots, there's two different ways that we can arrange them. So what about if we have a similar system with 3 particles. How many different ways can we arrange those? So if we think about this, we will have, if we decide that we want to have our green particle on the left, we can either put the purple particle next and then the orange particle, or with the green one still on the left, we could have put the orange one in next and then the purple. So just with the green on the left, we have 2 options. But we could also have chosen to put the purple one on the left, and then we again have 2 choices there, where we could have put the green one in next, followed by the orange, or the orange one in, followed by the green. And then we still have the options where orange is on the left, and then we could either put in purple and then green, or green and then purple. So just by adding 1 more particle to our system, going from 2 to 3, we've gone from 2 possible microstates to 6. And that would increase to 24 if we went to 4 particles. It's related to the factorial, if you're interested in the math side of things. So there become very quickly lots and lots and lots of ways that we can arrange things. And this is not allowing for any empty space in our system either, which can also complicate things further, but we don't really need to think about that to get the gist. But as we increase the number of particles in our system, we're increasing the number of ways that we can arrange them, which is leading to higher entropy in our system. So for chemical reactions, we can see this in a few examples. So we can assess, just based on how many particles, how many molecules are on each side of our reaction, whether we expect the entropy to increase or decrease. So for example, we can have calcium carbonate reacting to form calcium oxide and carbon dioxide. In this one, on the reactant side, we have only 1 particle, 1 molecule. But on the product side, we have 2. So going from 1 particle on the reactant side to 2 particles on the product side, we probably have more microstates in the products. So we can say that it is likely that the entropy change for this is positive, that the entropy is increasing as reactants are converted to products. So why don't you take a few minutes and try to identify for the next 3 reactions whether you expect delta S to be positive, negative, or approximately 0. So as we look at these next reactions, at this point, we're just comparing how many molecules are on each side. So one thing we want to be aware of is that we do factor in the coefficients to those numbers. So on the left-hand side of this reaction, we have 2 molecules of NH3. Remember that the coefficients are representing separate copies of the same molecule. So those are 2 independent particles. So we have 2 particles on the left. We have 1 nitrogen plus 3 hydrogen for a total of 4 particles. On the right. So once again, we have fewer on the reactant side, more on the product side, means that we have more possible microstates in the products. So as this reaction proceeds from reactants to products, the entropy is increasing. So delta S would be greater than 0 for this reaction as well. In the next one, we have 2 magnesium plus 1 oxygen for a total of 3 particles on the left and 2 magnesium oxide for 2 particles on the right. So this time we're going from more particles in our reactants to fewer in our products. So our product side probably has fewer microstates, meaning that the entropy decreases as this reaction proceeds. So delta S would be less than 0. And last but not least, our coefficient of 2 tells us that we have 2 molecules on the left and only 1 on the right. So we're taking those 2 particles and attaching them together so that they're only one thing, which means that we're going to have fewer possible microstates in our products than we did in our reactants. So as this reaction proceeds, the number of microstates decreases, which means that the entropy decreases. So delta S is less than 0 for this reaction as well. So the other factor that becomes really important when we're looking to assess the entropy change of a chemical reaction is the amount of energy. So the number of particles in the system was what we were just talking about, but the amount of energy in the system is also important. I defined a microstate towards the beginning of the video as a way to arrange the particles and energy in a system. So particles is one side of it, energy is the other. And the amount of energy is going to be related to our state of matter. We know that as a substance absorbs energy, absorbs heat, it gradually goes from a solid to a liquid to a gas. Gases are higher in energy than liquids, which are higher in energy than solids, as a general rule. So typically, more energy in your system also equals more microstates. So if we consider that same simple 2-particle system that we had earlier, and we bring some energy into the mix. So the simplest unit of energy is the quanta, is the smallest. It's like a photon of light. Quanta of energy is the smallest particle of energy that you can have. So if we put just 1 quantum of energy into this system, so if I consider this first microstate, where I have the blue particle on the left and the pink particle on the right, I have a choice of where to put that energy. I can have that energy, use a little star to represent energy. I can have that energy on the blue particle, or I can have that energy on the pink particle. Those are different microstates. So for the same arrangement of particles, so we have blue on the left, pink on the right, blue on the left, pink on the right. These 2 pictures have the same arrangement of particles, but they have a different arrangement of energy. I can either have the energy on the pink or the energy on the blue with my particles arranged this way. Those are now 2 different microstates because the energy is arranged differently between them. We also had another particle arrangement with the pink particle on the left, and I can once again have my quantum of energy on either the pink particle or the blue particle. So with 2 particles with just a single quantum of energy thrown in there, I now have 4 different microstates. I now have 4 different ways that I can arrange my particles and my energy differently in this system. If we look at the same thing with 2 quanta of energy, I now have even more choices. Let's try to keep this clear. Does this fit? close enough. So if we consider a two-particle system with two quanta of energy, so the top row is all the same particle arrangement, blue on the left, pink on the right, and then the bottom row has pink on the left, blue on the right. If I have two quanta of energy to distribute here, the most obvious version is kind of to put one on each, that I can put one quantum of energy on each of my particles. But a particle can have more than one. Particles change in energy all the time. They gain energy and lose energy. So I could have all of my energy on the blue particle and none on the pink, or I could also have all of my energy on the pink and none on the blue, or evenly split between the two. So for this same arrangement of particles, I have three different ways that I can arrange the energy in this system. And then same for the other particle arrangement. I can spread my energy out evenly between my two different particles. I can have all of it on the pink, or I can have all of it on the blue. So by adding more energy into the system, keeping the same number of particles, I have also increased the number of possible microstates. I've gone from having 4 microstates with only one quanta of energy to having 6 microstates when I put in 2. So how this applies to chemical reactions is most notably through our state of matter, where in general, solids are lower in energy and therefore entropy than liquids, which are lower than gases. So this is going from low energy to high energy, and therefore low entropy to high entropy for these states of matter. So if we're looking for how the entropy is changing in a chemical reaction, we can look to the states of matter for a clue as well. And this is often actually more important than number of particles, especially if a gas is involved. Solids and liquids, solids are lower in entropy than liquids, but not by a ton. Liquids are a lot lower than gases. So forming a gas as a product increases the entropy rather massively. Taking a gas and removing it as the products form is usually a huge decrease in entropy. But this is another thing that we can look at if we're going from a low energy phase to a high energy phase. Our entropy is going to increase. If we're going from a high energy phase to a low energy phase, our entropy is likely to decrease. So in an example like this, we can look at the states of matter listed and figure out, does it seem like we're generally increasing in energy of our states of matter, or are we decreasing in energy? So aqueous is pretty much the same as liquid. Since water is a liquid, those two things are pretty much equivalent in entropy. So we're going from something that is aqueous here to a liquid and a gas. So aqueous to liquid is pretty much no change, but this formation of a gas is going from something that's aqueous only on the reactant side to something pretty similar, a liquid, and a gas is much higher on the product side. So we have a higher energy state is going to give us more possible ways to arrange that energy, more possible microstates, is higher in entropy. So this is our higher energy phase here, which is telling us that delta S is likely positive for this reaction. So why don't you take a minute or two and try the other two reactions here. So for the next one, we have a liquid and a gas on the left side, and we have all gas on the product side. Specifically, we have 3 moles of gas on the left and 5 moles of gas on the right. So we've gone from having some of our stuff trapped in a liquid phase that is lower in energy, along with some gas, to producing more moles of gas ultimately. So that change in phase from some liquid with some gas to all gas is going to give us a large increase in entropy as well. And then last but not least, we have a solid and a gas reacting to form a solid and a liquid. So here, the solid on both sides is kind of a wash. We have gas versus liquid. Gas is going to be higher. So this time we're starting with more energy in our system, more entropy in our system, and it's decreasing as the reaction proceeds. So this is going to be a negative delta S, or a decrease in entropy as this reaction proceeds.